Last class, we talked about how f, f prime, and f double prime, the stuff we already talked about, helps us understand x, v, and a. Today, we have a situation where x and v are going to help us understand stuff about f. Something that's so important, so crazy. It was a very, very huge discovery. They call it the fundamental theorem of calculus. Okay, what we're going to learn today is called the fundamental theorem of calculus. And it has to deal with this problem right here. We got a curve, y equals 3x squared. We're talking about between 1 and 5. Here is 1 and 5, and we want to look at the area under this curve between 1 and 5. So here's like the visual representation of like the area, just that shaded region. Now, what class did you guys take that dealt with areas frequently? Geometry, right? And what did you use to find areas for the most part?
Square.
Yes, you used squares. No, but you had a what to find the area of a square? A formula. You had formulas to find areas of objects. Squares, rectangles, have straight sides. Trapezoids, straight sides. Circles. It's a curve, but it's a very specific type of curve. We had an area formula for that. Were you given an area formula for area under 3x squared? No. The answer is no. Okay. Were you given the area formula for the area under the sine graph? E to the x. Any curve? No. Okay. So this is why this was actually a very, very difficult problem to solve. And it wasn't solved until the invention of calculus, which is in the 1600s. Most of math's discoveries were in the BCs. Okay. So, like right now, you guys don't know what to do right now. Okay? But you will very shortly. Turns out you're closer to knowing the answer to this question than you think you are. Okay? And it's because we're going to use position and velocity. And I'm going to give you 2 word problems. Okay? The first word problem is going to help us answer the second word problem. Okay? Here's the first one. All right. Mr. Messner had to get away from you kids who vape in bathrooms. So he drove on I-35 at a velocity of 70 miles per hour from t equals 1 to t equals 3 hours. So that's over 2 hours. He traveled from mile marker, which is a position, of 234 to mile marker 374. You tell me how far did I travel, and you tell me the 2 ways in which you can get that distance. Okay? Because there are 2 ways to answer this question. Ready, set, go. Discuss it with your neighbors. Let's get the answer here.
70 times 2, 374 miles. Mile markers. Yeah. You go at 70 miles per hour. 2 hours. Well, yeah, I got that. Okay. Doing 100 miles an hour. How far do you go in an hour? That was a hard question.
That's one way. What's the other way? Oh. This is not as complicated as you think it is. It's easier than you think it is. Yeah. So mile markers. Think about mile markers. If I start at this mile marker and I travel to that mile marker, subtract the 2, find the change, and find the distance. So yeah, that's it. Here's the 2 ways. You have a velocity times a time. You took that 70 and you multiplied it by 2. Okay, that was my velocity times my time. Or you took 374 and subtracted 234. That was my ending position minus my starting position. I don't want to say it's my initial position. I want to say it's my starting position because my initial position usually references t equals 0. So I'm going to say start and end. And that came from my position at time 5 in this situation minus my position at time 1. Sorry, 3 minus my position at time 1. Okay, and you do those calculations here and here, you get 140. Cool. All right, now let's look at this graph that I provided. This is the graph of velocity. My velocity is 70 miles per hour. Okay. What would be the visual representation of this 140 when looking at this graph? Please discuss that with your neighbors. How can you see 140 by looking at that graph of velocity? Nope, not yet. How do you see it? Area. Underneath the line between 1 and 3 is an area of 140. Okay? So, this area is our distance that I traveled. Okay? Area under velocity is a visual representation of how far I travel. Okay, so in conclusion, just to let it sink home, I could do velocity times time, find a distance, really displacement. I could do an ending position minus a starting position. I could find distance. Okay. Next problem. Because I'm so frustrated about kids vaping in my bathroom, I can't get away from you kids fast enough. I decide to jump into a rocket-propelled car because I can. The rocket-propelled car travels at a velocity of 3t squared. I'll do miles per hour just so it's similar. Now, you don't know the exact location which I started. But it turns out it won't matter. The question is, how far did I travel between the first hour and the 5th hour? Okay. Now here we go. We know that we could think about velocity times time to be distance. And we know that the visual representation for that is the area under the velocity. Does that make sense? We following so far? Can I do V times T in this situation? Why not? V is not consistent. V is not 70 miles per hour over 2 hours. 70 times 2. That's easy. Here, my velocity is changing. So I'm accelerating. I'm traveling a velocity only for a very split second, and then I'm going faster at the next split second, and then faster at the next split second. And I could theoretically take these velocities and multiply them by the millisecond in which I'm traveling at the velocity, and then add them all together. Do we have time to do that? No. Okay. So this kind of approach, the velocity times time approach, I can't do. But we know that there is another approach. We know that we could either do this or what? Final position minus starting position. I don't want to say initial because I'm not starting at t equals 0 in this situation. I'm starting at t equals 1. Okay? So, or I could do my final position minus my starting position. Okay, answer this question. Get the answer. What's the number? How many miles did I travel? Nope. Did I give you any information about my final position and my starting position? It appears not, right? In the other problem, I gave you the mile markers. Here, I only gave you a velocity equation. It's not 72. Did I give you anything about position in the question?
Yes, 1 and 5. No, you didn't. So,
All I gave you was velocity. But do you know the relationship between velocity and position from last class? Oh, okay. So maybe we need to find a position equation, a position function. But now something's going to bug you once you find your position function. I did not give you an initial position, but I'm telling you it won't matter. Take any number that I put up there, 0, 50, or 111, or any other number, and plug it in for C. Do the math. No matter what you do, no matter what C you choose, you're going to get the same answer. Who got the answer? Did anybody get the answer? What did you get, Ms. Osberg? 124 is the correct answer. Did you get that answer too? Thank you, Ms. Vidi. Nothing. 124 is what we should get. Let's see if we can get it. Don't set it equal to 0. I'm just saying replace C with anything. It won't matter.
place C with 0?
Sure. That's not the correct antiderivative.
I did. Yeah. Maybe 5.
That would be
125.
that would be my final position minus my starting position. I started at t equals 1. My final position is at t equals 5. That's fine, because it's the same for both. We're talking about distance. It doesn't matter where I start to figure out how far I've traveled. If I started at mile marker 0, doesn't matter, versus mile marker 50. I traveled at this velocity over this time. Starting position won't matter. So here we go. You guys said, oh, wait, I know how to find x of t because of last class. I know x of t would be t cubed plus c. If you plug in 5, I'm just going to leave c there. I get 125 plus c. If I plug in 1, I get 1 plus c. Replace c. Now, this is the same c being used in both situations, right? This is not a situation where I have like 1 plus c and another plus c, and if I subtract them, I get a third c. This is the same number. You know, this could be 4. This could be 8. This could be 400. So, because it's the same number, when you subtract them, they go away. And you get 124. Okay, so I've traveled 124 miles. Still don't think that's far enough away. Anyways, I'll have to get in a faster car.
Kind of slow for 5 hours. That's really slow for 5 hours.
4 hours, actually, yeah.
4 hours, yeah.
Well, what's the difference between this situation and my previous situation? I started 0. Yeah. So after 1 hour, I'm going 3 miles per hour.
Rocket ship stinks.
My rocket ship stinks, yeah. Okay, well, let's go back. We had zero clue how to do this. We now know the answer to this. Okay? What's the answer here? What is the area under 3x squared from x is 1 to x is 5? This, my friends, is such a great discovery. They called it the fundamental theorem of calculus. What we did last semester, derivatives, tangent lines, seems to be completely unrelated to area under curve. Right? Completely unrelated, but turns out very much related. If you find the antiderivative of this curve and you find the change in the antiderivative, if I say find big F, and I find the change between big F of 5 and big F of 1, I will get my answer. Why? We are always going to, and I'm always going to reference this as the why, because instead of doing velocity times time, which you don't know, you're changing your approach to answering the question by doing ending position minus starting position. Does that make sense? Why this antiderivative works? Why this is a way to answer this question without having to do multiplication? Okay, here we go. The fundamental theorem of calculus equates areas under curves to changes in antiderivatives. We think of areas under curves as being like the velocity times time way of doing things. We think of change in antiderivatives as being the ending position minus a starting position. Okay? Now, to make sure, like you believe me, we can actually do this process for a function y equals 2x from 0 to 4. Okay, so I'm from 0 to 4, and we can do it two different ways. Now, in this case, like velocity times time, I'm not going to do my velocities times time because my velocity is changing as well. But we know velocity times time, the representation is what when I look at this graph? No, looking at the graph, what I see. Bad question. The area, okay? Is there a way to calculate the area of this region? It's a triangle. You can use a formula. So let's go ahead and just like calculate this area using a formula, area formula, 1/2 base times height, okay? This goes all the way up to 8 because it's y equals 2x. So 1/2, 4, 8, 16. But now, let's try the alternate approach. Let's try ending position minus starting position. Now, this is tricky because I didn't say this is velocity, but you're thinking, okay, this is my velocity. Velocity times the area. Take the antiderivative to get your position function. Okay, so what would be my position function? X squared plus c. C won't matter. In this situation, what is the time in which I end? 4. If you think about this axis as being our time axis, you're thinking of 4 minus What is the starting time? 0 in this case. So I have x squared plus c. Find it at 4. Find it at 0. 16 plus c minus 0 plus c. We got the same answer, though completely different ways. 4 being squared, coming from an antiderivative versus using an area formula. Okay? Now, I want you to remove this example and replace it with this example. Just as a situation we need to be wary of that we will discuss more next class. But for right now, you're just going to take my word for it. Okay, we got it copied down? Cool. Let's go straight to the kind of alternate approach, ending minus starting. So I'm going to take the antiderivative of this to get my x function. I get negative x squared plus 2x plus c. And it goes till t equals 4, and it starts at t equals 0, right? So let's plug in 4 and let's plug in 0. So I get negative 4 squared plus 2 times 4 plus c minus 0 plus 0 plus c. And I got negative 16 plus 8, which is negative 8. Why does that answer not sit well with us? Yeah, very good. How do you have a negative area? Well, what I'm going to tell you, and we'll talk about more why next class and in the future, is that if we are underneath the x-axis, our velocities are like negative, which means I'm moving to the left, and what actually we're finding is a displacement. For right now, just go with me. If you are underneath the x-axis, area is negative. So watch. If I did using triangle formulas, 1/2 base times height plus 1/2 a base of 3. For the second triangle, I would say that my height is negative 6. You're going to get the same answer. You're going to get 1 plus negative 9, and you get negative 8. Okay? We'll talk about more why negative numbers are okay. We're going to go back to just position, velocity, acceleration next class. We'll talk about distance versus displacement, and it'll be okay with you. No, we're going to say the answer is negative 8. Okay? So from now on, if you're underneath the x-axis, you're going to say the area is negative. Okay? Is it right? I mean, it depends on what you talk about. Just go with me for right now, okay? All right, thanks. Now, for those previous two examples, we could use formulas of triangles. For this one, you can't, okay? The whole velocity times time method, the whole geometry method, you can't do. But you guys could find the area under x squared between 0 and 1. Please find it. not 1. What is it, Ms. Shaw? 1/3 is correct. The area under x squared between 0 and 1 is 1/3. I'm not giving you a velocity graph. What am I giving you? A y equals x squared graph. Okay? But the idea is the same. You can pretend, Ms. Hoffman, that this is a velocity graph. You can pretend any graph is a velocity graph. And we know velocity times time, sometimes we can do it, sometimes we can't. And when we can't, we'll have to do ending position minus starting position. Like this situation, I'm going to have to find a position function. What is it? It's just big Y, the antiderivative of Y, 1/3 x cubed plus c. I plug in 1. I plug in 0. I get my answer. Okay? Okay. Now, we are going to kind of formalize this process. I'm sure some of you kind of wrote big Y equals, or maybe have been sticking with like V and X, and that's fine. But this is the notation that you'll see no matter where you go for what the process we are, what we're doing, okay? So I have a question. I got an area I want to find under 1/x. What would be the first step to find this area, knowing that it's a curve, the velocity is changing? I can't do this using a formula. What would be the first step? Very good. Take the antiderivative. What is the symbol we've been using for take the antiderivative? Yes, the integral squiggly guy. Okay, so we're going to start out by saying, okay, I need to take the antiderivative of 1/x. Right? That's what I need to do to answer this problem with respect to x. That's what I need to do to answer this problem. I need to take the antiderivative of this to get a position function, you know, if we consider this velocity. But after we do that, we need to worry about these numbers, 1 and 8. So instead of just leaving this blank, you're going to throw the number 1, your start, there, and the number 8 there, your end. And this is reminding you of the fundamental theorem of calculus, which is like you need to find the change in your antiderivative, your ending position minus your starting position. Okay? So I have an integral. I need to take the antiderivative. The next step is take the antiderivative. What's the antiderivative of 1/x?
Log x.
Yes, good. Log absolute x plus c. Now I'm going to throw something else at you here. You're going to put a line to the right of this. Just to remind you, hey, don't forget to plug in those numbers so that I have my ending position minus my starting position. Okay? Now, in all the previous problems, do we have to worry about C? No. I would advise you write it down so that when we do have to worry about C, you don't forget about it, but just put the plus C and then cross it off. You don't have to include it in this work when you find your ending position. Essentially, it's just the connection will hold minus your starting position, because the plus C's will cancel. What's the log of 1? 0. My answer is log 8. This is called a definite integral. that's just vocabulary. Okay, it's just like an integral defined as like, hey, it's not just take the antiderivative. It's actually, hey, use the antiderivative to find the area. Okay? Okay. So, you guys set up your definite integral and evaluate it so that you can find the area under e to the x between 0 and 3. Your first step is like, oh, I have to take the antiderivative of e to the x. So you write your integral with e to the x in it. You include your starting and your ending times. What was the antiderivative of e to the x? E to the x plus c. I don't like doing this example because like it doesn't look like we actually took the antiderivative, but we did. Anyways, whatever. We don't need to worry about the c. I get e cubed minus e to the 0. Is that 0? That's 1. Okay, so e cubed minus 1. Don't make that mistake. Not always when we plug in 0 will we get 0. Another example of when we plug in 0 not getting 0 is this one. This is my favorite one. What is the area under one hump of sine? It must be complex. It must involve pi's or something. You guys tell me. What is the area under one hump of sine? If you get an answer like 0 or -1, you know it's not correct. Let's think. Antiderivative of sine. The derivative of sine is cosine. Okay. The derivative of cosine is negative sine. Okay. So the antiderivative of sine must be which function's derivative is sine? Is it cosine? No, cosine's derivative is negative sine.
Yeah, so negative cosine.
Negative cosine.
You confused me with all.
Yeah, I'm sorry. I know one of you four was saying the wrong thing. I don't know who it was.
You were both saying negative cosine. Y'all were saying cosine.
All right, did we get the answer yet? What is the answer? Yes, very good. It's a negative cosine. Okay, so subtract negative cosine of 0.
Negative 1 minus 1. The answer is
No, it's not 0.
Yeah. It's not 0. Yeah, you just got to evaluate that. It's not 0. I see area here.
No. Negative 1 plus positive.
It is not 0, guys. Look. It's not 0. Look at it. The answer's 2. The answer's 2. The answer's 2. Isn't that crazy? The area under the sine graph from 0 to pi, one hump of the sine graph is just 2. That's too simple of an answer. But math works in mysterious ways. Yes, that's correct. I will continue this lesson because there's more we haven't gotten to. Watch. The antiderivative of sine is negative cosine. It's now negative cosine pi minus negative cosine 0, because I don't have to worry about the c. Cosine of pi is negative 1. This turns into positive 1. Cosine of 0 is 1, so this is minus negative 1. That turns into positive 2. I'll get you. Okay, continuing on. If you were just given an integral, it's already setting it up for you to succeed, okay? You just have to know it's like, oh, here is, you know, an integral that you know is an antiderivative. The more important thing is being able to understand what you are finding when you get your answer. Like when I get this number as my answer, what is that representing? Area. That's it. Area under 1 over x squared from 1 to 2. Okay, so now like we weren't given the graph, we were just given the integral already set up. But when we get our answer, we'll know what it means. We take the antiderivative of 1 over x squared. Remember, you do not use logs for this antiderivative. It's x to the negative second. You add 1, multiply by the reciprocal. The antiderivative is negative 1 over x. You would evaluate this between 1 and 2. You don't need the plus c. You get negative 1/2 minus negative 1 over 1. The answer ends up being positive 1/2. The area under 1 over x squared is positive 1/2. Okay, same thing. You think of this as your velocity function. You take the antiderivative to find your position function. You use this line. We understand that this is like our ending position versus our starting position. I don't want to say initial because we don't start at t equals 0 all the time. You get 27 minus 9 plus 6. Don't worry about the plus c. Minus 8 minus 4 plus 4. So that's 1824 minus 8 is 16. Now, really important, notice what I'm doing here. When you subtract your starting position, so my ending position minus our starting position, that starting position, if there's multiple things in it, needs to be in a big set of parentheses. Grab the notes while you're at it. And grab the last homework that you missed too. So that's why I have this entire thing in parentheses. So don't just subtract 8, then subtract 4, then add 4, because you could distribute this negative if you wanted to. Okay, we're going to skip the next couple. I actually don't think they're that important. We're going to move on to this. Grab stuff. Man, what's going on here? It asks me to find k. Take this equation and translate it into something visual. And then, like, tell me, what is the question asking? Yeah, it's asking what the final time is, really. So you have this 3x squared from 2 to some number k. This area here needs to be 12. Find k so that it's true. Does that make sense? You don't have to do this, but I'd like you to do it just so you understand what's going on here. You might be like, how do we do it now? Well, you have an integral. What do you think we should do first? Take the antiderivative. Okay, I got x cubed plus c. I got 2 as my starting time and k as my ending time. That has to equal 12. Well, my ending position would be my ending time plugged in. I got the k cubed. I don't have to worry about the plus c. I subtract my starting position, so that's my starting time plugged into this. I get 8. Is this something you can solve? Yep. Turns out, from 2 to the cubed root of 20, the area under 3x squared is 12. Pretty cool. Next page. Oh, this looks really complex. It's not. Don't be intimidated. Integral, f prime. What should we do first? Ms. Kalina? Antiderivative. What's the antiderivative of f prime? F. Okay, so I got f of x plus c. Do we need it? Nah. Get rid of that plus c. That's my position function. Starting time 1, ending time 3. Find your position at time 3. Subtract your position at time 1. We'll look up here. I have information about f. F of 3 is -4. F of 1 is 5. I get -9. These are easy. Do the next one real quick. Now the last one. What intimidates you a little bit when you look at this last one? Yeah, 2 is the starting time. We like to think about these as like time. And 3 is my ending. 3 is my starting time. 2 is my ending time. It's like I'm starting at t equals 3 and I'm ending at t equals 2. How does that work? Well, don't worry about it. It's like, how far did you travel, last hour rather than this upcoming hour or something? Just go ahead and go with it. Now, when we talk about areas, we'll talk about how that changes things, but we don't have to worry about that just yet. So the antiderivative of f prime is f. Just keep everything the same. You would have to do my ending position, which will come from my ending time at 2, and then subtract my starting position coming from my starting time at 3. So as long as you keep things all in order, you should be fine. I have 2 minus -4, which is 6. Okay? The next two seem intimidated, but again, don't be intimidated. We see an integral. Integral tells you what? Antiderivative. What is the antiderivative of 3 minus 2f prime? What's the antiderivative of 3? 3x. Oh, okay. Yeah, you're right. 3x. What's the antiderivative of 2f prime? 2f. Okay. So I get 0 minus -7, +7. Anybody else get that? Put parentheses around our starting. Make sure we put parentheses around our starting position. Forgot the 2. That was it. Last one. What's the antiderivative of x? Yes. Good. So like it's just no big deal. If you know how to take antiderivatives, we spent all last unit before the break taking antiderivatives. Well, now we're just using them in such a way that we didn't think we'd be able to have anything to do with one another, but turns out antiderivatives can help us find areas. F of 3 is -4. I'm not even going to bother doing these calculations. Whatever that is. Okay? So cool. We started out with a question that we thought we had no idea had to do. We then realized that if we think about this in terms of, and we're calculating distance, because we know the relationship of velocity and position, how position is the antiderivative of velocity, we're able to figure out this question and then apply the same kind of concepts to answer the question about how to find the area under any curve. It's pretty neat. So neat, they called it the fundamental theorem of calculus.